Hello everyone, welcome to my channel Chemistry by ANR. This topic is on isomerism in coordination compounds. What are isomers? Isomers are two or more compounds that have same chemical formula but different arrangement of atoms. The chemical formula remains same, arrangement of atoms are different. Now, since the arrangement of atoms are different, they differ in their physical and the chemical properties. What are the types of isomerism? Isomerism in coordination compounds can be of two types. So as you are studying, you can form your own flow chart. So you can say, okay, isomerism in coordination compounds are of two types. And what are they? One is stereoisomerism. So you can say this is stereoisomerism, and the other is structural isomerism. So this is the second part, which is known as structural isomerism. In stereoisomerism, there are two classifications. One is geometrical isomerism and the other is optical isomerism. So geometrical and optical are the two divisions of stereoisomers. Remember one thing, that stereoisomer means they differ in the three-dimensional or spatial arrangement representation. So, geometrical isomerism can be again, say cis and trans. So, it can be either cis or trans geometrical isomer, or it can be FAC and MER, facial and meridional. So, FAC and MER, these are two types again. Optical isomerism can be dextro and levo, dextro-rotatory and levo-rotatory. So these are the two optical isomer. Structural isomerism can arise due to the different representation of the formula or different representation of the structure. They can be linkage isomer, coordination isomer, ionization isomer, and solvate isomer. So it can be linkage isomer, which generally arises in ambidentate ligands. So linkage isomer, coordination isomer, differing in the coordination sphere, we'll elaborate it later on. And it can be, say, ionization isomer, and it can be, the last thing is solvate isomer. So solvate isomer, if the solvent is water, it can be hydrate isomer as well. So this is the flow chart for isomerism. So let us elaborate one by one. So when you see stereoisomerism, the first thing that comes for discussion is geometric isomerism. Now, what is geometric isomerism? The first point which is important is this type of isomerism arises in heteroleptic complexes. That means those coordination compounds where more than one kind of ligand is attached to the central metal atom or ion. And these types of isomerism is due to the different possibilities in the arrangement, geometrical arrangement of the ligands. So let us see on which type of isomerism, which type of compounds exhibit these isomerism. So first thing that we will discuss is they are found with coordination numbers 4 and 6. That means coordination number 4 and coordination number 6. They will exhibit these types of isomerism. Square planar complex means coordination number equal to 4, and having this type of formula, that is MX2L2. This type of formula where X and L are unidentate ligand. So these two type of ligands are there. X is one type of ligand, and L is another type of ligand where both are unidentate ligands. So here we can see, since the denticity is 1, so the coordination number over here is 2 plus 2 equal to 4, because both are unidentate ligands. They are unidentate ligands. Now, another thing is they can exist as cis and trans form. So X, if I say like this, let us elaborate, like MX2L2. If over here X is equal to Cl and L is equal to NH3, then we can say that it is of this form. If these two are on the same side, it is cis, and if they are diagonally opposite, then it is a trans isomer. Now, other square planar complexes can be of the following types. Metal attached with 4 different type of ligands, and the 4 different types of ligands, they are all unidentate ligand. So here we can see it shows 3 isomers, out of which 2 are cis and 1 is trans. So let us try to draw the cis and the trans isomers. Okay, so such isomerism is not possible for a tetrahedral geometry, but similar behavior is possible for octahedral geometry. You can try and check out whether you are able to draw or not. So square planar complexes showing cis trans, they are of MX2L2 type. They can be MABXL type, where they are all unidentate ligand. And here we can see that this type of isomerism is not possible for tetrahedral geometry, but this type of isomerism is possible for octahedral complexes. We will try to represent them. See, geometrical isomers over here of PTNH3 whole twice and Cl2. This is which type? This one is which type? This is of MX2L2 type. Now over here, if I say that this is a cis and this is a trans, it is of which type? This is a coordination number equal to 6, which is octahedral complex. In an octahedral complex, you can see that if Cl, which the two groups where I can see that these two are anti to each other at a maximum distance apart, then it is a trans isomer. And if it is in adjacent positions like this, it is a cis isomer. So this is a type of geometrical isomer which can be represented in octahedral complex. Next, we can talk about this type of isomerism arising in didentate ligands having a denticity of 2. Like over here, nitrogen is having lone pair, both the nitrogen is having lone pair in ethane 1, 2 diamine, and it's a didentate ligand. So we can represent it as LL, having 2 donor site. So here, what is your coordination number? If X is your unidentate ligand and this is your didentate ligand, then in that case the coordination number is equal to 2 plus 2 into 2, which is equal to 6. So the geometry which is possible is octahedral. Now we can see that if this is the octahedral geometry, this is the octahedral geometry that you can see, it can exist as cis and trans form. Now it will be easy for you if you try to locate, I will say, if you try to locate the Cl atoms anti to each other, then this becomes trans. Cl atom adjacent to each other, then this becomes cis. Now, what about the didentate ligand? This is your ethylene diamine. Nitrogen is the donor atom. So, En can be abbreviated and can be represented in this manner. If you really want to see how the linkage was, it can be represented in this manner. You write here one Cl, write here another Cl, and make dotted lines to show this plane. And then remember that leftover bonds are these having En and this having En. Now again, if you want to see the donor atoms, this is the cis form. It can be drawn in this manner. So it is CO having Cl on adjacent positions, and En means NH2, NH2, CH2, CH2, and this is again NH2. It can be represented in this manner. So here again, this can be NH2, CH2, CH2, and NH2 written joined in this manner. This is again your cis isomer. Looks complicated, isn't it? But it is not at all complicated if you understand and draw the structure. Now, trans isomer. Try for your own. I said one thing, that for a trans isomer, try to locate the Cl atoms anti to each other. So first try to locate that. This is the Cl and this is anti to it. So this is your trans isomer. Now you know it is monodentate. The other two, which is didentate ligand, is ethane 1,2 diamine. So you make abbreviations here En, make another abbreviation here En. Now if you say that how is it actually bonded, so for that you draw it in this manner. Make Cl here, make Cl on the anti position, and then join the square plane in this manner and make NH2, CH2, CH2, another NH2 here joined. So make here NH2, make CH2, CH2, and NH2 joined in this manner. So this is your trans isomer. Now, moving on to the next part. Another type of geometrical isomerism occurs in octahedral coordination entity. Of which type? Ma3B3 type. Now you can see NH3 and NO2. So you may think, what is the coordination number? Both of them are unidentate. So the coordination number is equal to 3 plus 3 equal to 6, which is octahedral structure, octahedral geometry. Now here, if this type of isomer is drawn in two representations where the donor, the three donor atoms of the same ligand occupy adjacent position at the corner of an octahedral face, then we will say facial. So I said that the three donor atoms of same ligand occupy adjacent position at the corners of an octahedral face, then it will be facial isomer or FAC isomer. So we can see the three donor sites N, NO2, NO2 and NO2. They are in adjacent positions. So it is a facial isomer. Now, if the positions are around the meridian of the octahedron, so we will say if it is around the meridian of the octahedron, then it is meridional or mer isomer. So we can see this is your meridian, this part is your meridian, and there are three NO2 attached in this manner. So it is a mer isomer. You may think, which is the meridian? See, it is passing through the central metal, covering up the three edges. So that is your meridian, which forms the mer isomer. So this is one very important question. Why is the geometrical isomerism not possible possible in tetrahedral complex, having two different types of unidentate ligand coordinated with the central metal atom, having two different types of unidentate ligand, that means M, and having two different type of unidentate ligand, that means what? It can be A, B, C, D. This type means four different, that is a different thing. But if I say two different types, that means A2, B2, this type, this is not possible. Why is it so? Because if you try to locate them, what will happen? Their relative position will appear to be same with respect to each other. When you observe it in 3 dimension, you try to rotate the compound and view it from all direction, you will see you don't get a different representation. It seems to be the same. Now, optical isomerism, they are what? They are the dextroform and the levoform. They are the mirror images and are not superimposable, non-superimposable mirror images of each other. That is, they are enantiomers. The molecules or ions that cannot be superimposed are called chiral. So obviously, as we have seen in the previous organic chapters, same thing, the first point will be the presence of a chiral center in the structure of the molecule. The presence of a chiral center, a center with 4 different valencies. Second thing will be they will form mirror image, but these mirror images will be non-superimposable. So non-superimposable mirror images, and they are known as enantiomers. So if we try to draw them, the two forms are dextro, which is represented as D, small d, not a capital D, because capital D means configuration and small d means optical rotation, and the other is levo with a small l. Depending on the direction they rotate the plane polarized light. That is, upon the direction they rotate the plane or polarized light in a polarimeter. So if it is capable of rotating the plane polarized light towards right side, then it is a dextro, and if it is capable of rotating the plane polarized light towards left, then it is a levo, and it's represented by small d and small l respectively. Now, optical isomerism is common in octahedral complexes involving didentate ligand. Then it is of what type? Octahedral complex involving didentate ligand. So didentate means denticity is 2. So this is of what type? Here again we can say if denticity is 2, then here the coordination number ethylene diamine denticity 2 having 3 in number is 6. So it is an octahedral complex. So ethylene diamine with dextro. So how can you draw it? You will first draw in this manner and then try to make the EN linkages. When you see the mirror image, remember one thing, the group that is close to the mirror in the mirror image will remain close. That is, away from the mirror in the mirror image will also go away. So the groups that are closer will remain close, the group that is away will go away only. And these two mirror images are non-superimposable, just like your left hand and right hand. They are the mirror images. You lift up your right hand and place it just above your left hand. Do you see them getting eclipsed? No, not at all. So they are non-superimposable mirror images. Optical isomers of this type. So we can see the dextro and the levo forms. The previous case was COEN whole thrice, having only one didentate ligand but 3 in number. Now it is of what type? Now it is having PtCl2En whole twice. So Cl is unidentate, so the coordination number will be equal to, for Cl2 plus for En it is didentate, so 2 into 2, because 2 such didentate ligands are present. So 2 plus 4, which is equal to 6, and if it is 6, it should be octahedral geometry. So the geometry is octahedral. So again you draw it in this manner. It is this plane, and now you can see that in the dextro form, one of the dextro form tried to keep the Cl in adjacent positions, just the way you were trying to do the cis form, and then draw the mirror image. So the group that was close to the mirror remains close. The group that was far from the mirror is far. So in that manner, if you draw the mirror image, see, it is non-superimposable. So that what is happening is in cis isomer showing optical activity. So this is your cis isomer showing optical activity of this type. So this is what you have seen in optical isomerism. Next, draw the structures of geometrical isomers of this compound. First, you have to see what is the coordination number, which is very much evident because both are unidentate. So NH3 के लिए 2 and Cn minus के लिए 4, which is equal to 6. So since it is 6, it is octahedral geometry. You try to locate the cis isomer, the one which is 2 in number. Keep it in adjacent position. NH3 is in adjacent position. So this is your cis isomer. NH3 is in anti position. So it is your trans isomer. So always try to locate the one which is 2 in number, less in number, in order to make a cis or a trans isomer. Moving on to the next, out of the following two coordination entities, these are the two coordination entities, which is a chiral one. Chiral means having 4 different valencies and optically active. If it is chiral, then it will be capable of producing non-superimposable mirror images, that is enantiomer. The two entities that are represented are what? They are the cis and the trans form. Out of these two, which is actually optically active? We can see out of this, the cis isomer is optically active. Why is it so? Because it can produce, the cis isomer can produce non-superimposable mirror images of itself. Non-superimposable mirror images of itself. So you have seen this in the previous case, non-superimposable mirror images. Just like this, the cis isomer can form. It is better if you can show the non-superimposable mirror image, keeping in mind that the group that is close will remain close. The group that is far will go far. So Cl goes far. And what remains close is what? Your oxalate ion. So this is your oxalate ion, and here again this is your oxalate. This is the ligand. So this is the other isomer, 3 minus. So the cis form is showing geometrical isomerism. The trans cannot show geometrical isomerism because its mirror images is superimposable. This will produce superimposable mirror image, and so it will not be able to give you the optical activity. Okay, linkage isomer. Linkage isomer means, I told you, it is specially for those type of compounds having ambidentate ligand with 2 donor sites, like NCS minus. It is what? it is see, if it is NCS, then it is thiocyanate and if it is SCN, it is thiocyanate. So here, once N is the donor atom and in the other case, S is the donor atom. So let us see how it is obtained. The question can be of many types. Suppose anyone tells you to draw, say, the linkage isomer of this particular compound which I have underlined or highlighted. The linkage isomer of this particular compound will be NH3 whole 5, such which is ambidented. NO2 is ambidented. So I can write ONO and then I can keep the other things all same. So try to name them, name the isomers. Over here it is what? Pentamine. Pentamine, then comes your nitrito, so nitrito N it is, cobalt because this is your positive sphere, keep the space for oxidation state and then write the counter ion which is chloride. See what will be in the oxidation state. If you consider X for cobalt, NH3 is neutral, NO2 is -1 and this is equal to 2 plus. So it will be X is equal to +3. So cobalt 3 chloride. What will be the IUPAC name of its linkage isomer? Only in place of nitrito N it will be nitrito O. Rest of the things will remain unchanged. Now, coordination isomerism means it arises from the interchange of ligand between cationic and anionic entities of different metal ions present in the complex. Let us see the example. Over here we can see NH3 is bound to CO2 plus, Cn minus is bound to Cr3 plus. Now, if we try to draw the say the coordination isomerism, just change the position of the central metal and see the ligands are attached to two different metals now. In this case, previous case NH3 was attached to CO. Now in the next isomer NH3 is attached to Cr and here Cn was attached to Cr and now Cn is attached to CO. So this is what is known as coordination isomer. If you try to actually name them, how can be the naming? Say we can try with one of the isomer. This will be what? This will be hexaamine. Hexaamine cobalt, because it is in the positive part. We are keeping space for writing oxidation state. This is hexacyanido. So hexacyanido, negative part written later on. So it will be chromate, we will say, not chromium. So chromate. And what will be the oxidation state? So NH3 is neutral, Cn is -1, so 6 are there. This is divided into two spheres. So this will be 3 and 3. Both the side. So now ionization isomerism. Which type of compounds will show ionization isomerism? Keep in mind it arises when the counter ion in a complex salt is itself a potential ligand. That means the counter ion or the ion which is ionized, the part which is ionizable, can also act as a ligand. See, SO4 is acting as a ligand here and its isomer in that SO4 is acting as a counter ion. So these are ionization isomer. Solvate isomerism occurs when you have the solvent molecule as ligand or as the counterpart, if not the ion. So if H2O is used, it is hydrate isomerism, and here we can see H2O as solvent. Water is used as a solvent here, and the solvent isomer, they differ in the linkage. Okay, so whether it is the solvent molecule is directly bonded or it is just present as a free solvent molecule in the crystal lattice as water of crystallization itself. So this color is violet of this complex. The color changes to gray-green. You may be asked the reason behind it. It is what the H2O molecule was present solely as a ligand, was bonded to the central Cr atom. When it is violet in color, it was acting as a ligand solely, totally. And the coordination number is also equal to 6 over here. Over here, coordination number remains same. It is 6, but H2O, one molecule, is present as water of crystallization. It remains in the crystal lattice, but not as a ligand completely. One molecule is remaining as a free solvent. So this type of isomerism is arising when the solvent gets bonded in a different manner in the crystal lattice. So this is an application question which is very important. In text question, indicate the types of isomerism exhibited by the following complexes. Draw their structure. What type of isomerism is exhibited? Before you start answering this, I will always tell you that first see what is the coordination number. In this, oxalate C2O4 2- is didentate. So the coordination number is equal to 2 plus 2 into 2, which is equal to 6, an octahedral complex. So the geometrical isomer can be cis and trans. Keep in mind the one which is less in number, try to locate it in adjacent position for cis, try to locate it in anti position for trans in order to draw it properly. The next is, it will show optical isomer here. Okay, which one? The cis form. The cis form will show the optical isomer. The trans form will not give non-superimposable mirror image. So keep this thing in mind that when you are drawing the geometrical isomer, this is the cis form and this cis form is giving optical isomer. So draw the dextro and the levo forms. How? If one is dextro, the other is levo, you don't know which is which. So the two optical isomers that can exist are this. So in the next case, here COEN whole thrice. So what is the coordination number? Here the coordination number is 2 into 3, which is equal to 6. So it is octahedral. Again, you need to see the two mirror images. If it is a octahedral complex, it is not of the type it is having two different ligands. Okay, it is only one ligand, but its density is 2. So the two optical isomers will be like this. In the next case, again, apply ionization isomerism, apply linkage isomerism. Why ionization isomerism? You can see that the ligand is becoming the counterpart over here. Linkage isomer NO2 is there, so you can write ONO over here. So like this you have to apply the concept. Now this is very important question. You have to give evidence that these are ionization isomer. If these are ionization isomer in this particular compound, it should actually give the test for sulfate. You can use barium chloride test, and in this particular compound it should give the test for chloride, and you can use silver nitrate test just as you use in your practical. So what is the test? For sulfate over here, using barium chloride, you will just a minute, here you will get a white PPT of barium sulfate. You can use lead acetate test, you will get a white PPT of lead sulfate. For chloride, you can use silver nitrate test, that is dilute HNO3, heat it, cool it, and then use silver nitrate, and you will get a white PPT of silver chloride, which is actually, this silver chloride is completely soluble in NH4OH, aqueous NH4OH, and this is the test for the chloride ion. So remember, evidence means you have to give a test for the counter ion. So till this, see you in the next module. Till then, bye all of you.